In this video, we're going to explore the idea of log linear, or sometimes called semi-log plots. So let's assume we have a function that we know, say the number of neutrons in some sample, and it's growing exponentially. And in particular, it's growing as this function, 5 times 10 to the power of t over 2, where t is measured in seconds, say. So we could just do some quick calculations for different times and see what happens to the number of neutrons as a function of time. And we can see that indeed it grows exponentially. Indeed, the number of neutrons are growing quite fast. So if you plot this on a normal plot, then what you'll see is what looks like relatively flat to begin with, and then very rapid growth as you go out to later times. The problem with plotting the data in this way is it's really hard to see that this is an exponential, and it's also really hard to extract the features of the exponential function from this sort of plot. All exponentials kind of look similar to each other when we plot in this way. They just look like they grow really rapidly. Also, this plot really just flattens the first couple data points because they're relatively small compared to the last few data points. So this isn't really a great way to plot data in a way that allows us to see the trends in the data. Instead, what we're going to do is we're actually going to take the log base 10 of n. When we take the log base 10 of n, well, we can just calculate what that is for the times that we had before in this table. And then we can plot the log base 10 of n versus t. It's not real obvious that that is a good thing to do, but it turns out if you do that, in this case, you get something that looks like this plot. You get a straight line of the log base 10 of n versus t, as opposed to the sharp exponential curve that we had when we just plotted n of t versus t. This is one of the benefits of log plots. Log plots allow us to see an exponential behavior as a straight line. So if you do a log linear plot, you can see that what would have been exponential is just some nice straight line, and the slope will tell you features about the exponential, and the intercept will tell you features about the function or the initial condition in your exponential. So in particular, let's imagine that we took this function n of t, and let's see how the slope and the intercept relate to the quantities in that function. So our function n of t is 5 times 10 to the power t over 2. So let's take the base 10 log of this on both sides. On the left side, we just have base 10 log of n. On the right-hand side, we're taking the base 10 log of that. And then remembering our rules of logs, so if we have two things that are multiplied inside of a log, that means we can add the logs separately. So we can add the log base 10 of 5 and the log base 10 of 10 to the power t over 2. Well, there's another rule about logs, which is when there's an exponential inside of a log, that exponential comes out front. And so that second term, I can actually write as t over 2 times log base 10 of 10. The first term, if you just evaluate that, log base 10 of 5 is somewhere around 0.7 for our purposes at least here. And now that last term, t over 2 log base 10 of 10, well, log base 10 of 10 is just by definition 1. And so what power of 10 do you need to get to 10? Well, you just need a power of 1. And so that simplifies to 0.7 plus 1/2 t. And so we found that by taking the log base 10 of n, we turned an exponential function into, well, it turned it into a linear relationship between log base 10 of n and t. The intercept is given by the initial condition at t equal to 0 for our n of t. And the slope of the linear line is telling us the factor up in the exponential. Okay, so that way we can extract data about our exponential by taking the data and instead plotting the log base 10 of n versus t. I also want to introduce the idea of log linear axes, because this is an alternative way and a very useful way of displaying the same data. So in the plot that we have here, the log linear plot that we have here, we have plotted on the vertical axis log base 10 of n. But that's not a really intuitive number to work with, log base 10 of n. It's really more intuitive to work with n itself. That's something that we're more naturally used to. And so a common way to do this is to take that vertical axis, that log axis, and instead write it in terms of n, but now it's really kind of secretly log base n, but we're writing the actual values of n in place. So in particular, we have n is equal to 1 down at the bottom. That would be log base 10 of n is 0, for example. So that was our horizontal axis in the previous plot. And then the n is equal to 10 line is log base 10 of n is equal to 1 line. And so you can see that each major division that I've written, 1, 10, 100, 1,000, is in log base 10 of n, it's 1, 2, 3, 4. So it's the same plot that we had before, except now I'm writing it in terms of its original n values. There is something a little funny about this plot, though, that you can tell that the minor tick marks that we've made here are kind of scrunched up as you get higher up on the scale. And that's because when you're taking the log of, say, 2 versus the log of 9, then those numbers kind of get scrunched up to the, say, log base 9, or log base 10 of 9 is really close to log base 10 of 10. And so the spacing on the log axis is not very linear. And so, but the lines here are individual steps in n. So I've marked, say, n equal to 2, 3, 4, and 5. You can see how they kind of scrunch up as you get closer to 10. The line right above 10 is actually 20. And so then it's 20, 30, 40, 50, and so on. And the line above 100 is 200, and so on and so forth. So it takes a little practice to learn how to read a log linear axis, but it's a really efficient way of plotting the data. So let's show that if we plot that same data that we had for t and n on this plot, this log linear plot, but with log linear axes, that we'll get the same straight line that we had before. So the data point 0, 5, so t equal to 0, n equal to 5, if I locate that on my graph, that should be just right here. My next data point, 1 and 15.8, so t equal to 1, n is equal to 15.8. Well, 15.8 is somewhere between 10 and 20. And it's going to be a little on the, a little bit above middle here because of the way that the log linear axes work. And so it's going to be somewhere around there. And n equal to, excuse me, t equals to 2, we'll have n is equal to 50. So that looks like it's right there. And so on. So I can put in the other data points in the same way. And you can see that we do indeed get a straight line. And this straight line, the slope of that straight line, is giving us the power of the exponential relationship. And then the intercept of this straight line is giving us the initial condition, as we expected. So this is another useful way of plotting that same data.